Okay, welcome back. This is, so what are we going to do today? 6.1, it's on set theory. Okay. If you're going to continue and become like a math major and stuff like that, this is extremely, in my opinion, very important. They should dedicate an entire class to the subject before you get too deep into topics like topology and advanced calculus and real analysis. Okay, so there's going to be, I hope, a lot of stuff that you already know. I hope. So maybe I should start with stuff you already should know. So we're going to have working definitions. Like we need to use the stuff in proofs. And it'll be rigorous. Okay, so I'm assuming you kind of already know things like intersections and unions. So just off the top of my head, here's two sets, and for example, A union B. That just means the element is either in A or in B. And what you're doing is just basically taking every element that's out there. In sets, we don't write repeated elements. Okay? So A union B would be 1, 2, 3, 4. Just basically everything that's in A and everything that's in B. A intersect B. Those are the items that are in both. Okay, so that would be 2 and 3. What else? A complement. Okay, so in order to know something like a complement, we kind of have to be aware of this universe of elements where these other sets exist. So let's just say the universe of elements is the set 1, 2, 3, 4, 5, 6. Okay. So a complement would be everything that's not in A. All right, and that would be basically U and then take away A. And we'll also have a difference kind of operation. So a complement is going to be 4, 5, 6. What else? So yeah, like I was saying, A minus B. So that's basically just take all of the stuff that's in B out of A. So we'll have just 1 in there. Okay, so I'm hoping that this stuff isn't rocket science. The book kind of gets carried away with this kind of stuff, and it's just, this is very elementary, so don't take it for granted. Oh, I did like 20 web assigned homeworks in set theory like this. These are elementary. Okay, these are elementary. Okay, some weird things. So weirdness. You can have sets inside of sets. So let's say I have the set A, and it's has some elements in here, and elements can be sets as well. So you can have an element here. That's the set that contains 2. Okay. So there's some weirdness going on. Okay, let's make another set that looks a lot like that, and we'll just put the element 2 in here. Okay, okay, so what is A intersect B? Well, the only thing that's common to both of them, and you may say, well, what about this weird guy here? That turns out to be different from the element 2. This thing is just the number 2. So I was saying the element 2. This thing is the set that contains the element 2. Maybe something that would help you figure this out. If we want to know the number of things in that set, and some books write it pound symbol A for the number of things in A. How many things are actually in here? Well, there's only 1, 2, 3 things in there, right? So there's the element 1, the element 2, and then the set containing the element 2. So there's just 3 things in there. 3. Okay, so for the intersection of A and B, each of them has the same element 2. So this would just be 2. Okay. Right. There's other weird sort of things, like then they could ask. They have this idea of subsets. Okay, so maybe I should go back to the original example here and ask, is A a subset of B? Okay. And in this case, you could look at those subsets as kind of like less than or equal to symbols. It's kind of, they have the same sort of abstract properties. And it's like a partial order or something like that. Or so is A basically less than or equal to B? Does A have all the same junk in it as B? And if it's a proper subset, then B would have things in it that are not in A. In this case, no, because A has the item 1 in there. Let's make a third set. So C equals 2, 3. In this case, C is a subset of B. Okay. So yes. And it's not only a subset, but it's a proper subset. And some books will write that as C is a proper subset of B. Okay, but you won't see that all the time. And in general, if you get in a book that's using a lot of set theory, hopefully they have an introduction where they define all their symbols. And you just go there. Okay, okay, so there's the idea of being an element, and then there's the idea of being a subset. So here, is B a subset of sorry, I just woke up, A? And yes, it is, right? Every element that's in B is an element of A, so yes. Is B a proper subset of A? So a proper subset. And yes, every element in B is in an A, and secondly, there's items in A that aren't in B. So yes, it is a proper subset. Okay, then there's weirdness with regards to elements versus being an element of versus being a subset of. So here's some weirdness. Is 2 an element of A? Yeah, the element 2 is inside of A, so yes. Is the set containing 2 an element of A? Yeah, that thing is inside of A. It's sitting right there. Okay. Is 2 a subset of A? Yeah, B is a subset of A. And the confusing thing is it's not about this at this point, right? You can make another set, call it set C, and define that to be the set that contains a set 2. And in that case, then you could say C, which is equal to the set that contains 2, is a subset of A. Okay. How about this one then? Is the set that contains 2 an element of B? And no, it's not, right? B only has one element. It just has the element 2. It does not have the set that contains 2. Okay, there's something called an empty set, and the empty set is a subset of every set. Okay, so what is the empty set? And this is more weirdness. What is, I had a brain issue there. What is the empty set? The empty set is a set that contains nothing. And the way I think of it is to think of it as an empty box. Okay, so I order a lot of stuff from Amazon now. I don't really leave my house anymore, and so I have tons of boxes. Okay, so let's say this thing represents a box. Okay? And it came from Amazon, and you know it probably had like some of my medications in there and stuff like that. Okay. Okay. So this empty box, I'm going to say represents the empty set, which is sometimes called also the null set. Null set, or it's the empty set. And so you can also just write it as like that. Okay. All right. I have to recycle my boxes, right? So what I do when I recycle my boxes is try to put them inside of each other, because I don't want to upset the garbage man. Right? The garbage man is my friend. He comes to my house, picks up my stuff, takes it away. So what I do is kind of just take my boxes and put them inside of each other. Sometimes they look like this. Maybe there's another empty one here, and then I got a guy over here, and maybe I put a couple boxes inside of him. Okay, so what the heck is this thing? Well, you can notate it in set theory. You can say it's a set, okay, that contains 3 sets. Okay, so I'm going to need a big one here. And then there's this empty one here. And then there's this one that contains 3 empty sets. This first empty set contains 2 empty sets, such that the second empty set contains 2 more. Okay. When you see something like this in like challenge problems and stuff like that, the way they're going to typically write it is for those innermost empty sets, they'll just write the null set. Okay, so for inside of this first set that's in the big set, there's a null set, and then there's a set that contains 2 null sets. Oops. Then the second one is just the null set. So I'm just going through and I'm doing at the top of the page this substitution here. Then the third set contains 3 null sets. Okay, so it's a lot of fun. You can make up your own kind of null sets. If you've not done the 10-point extra credit, I would love that. Go and get a bunch of boxes and make one of these things. You know, take a picture of it and then rewrite it in set notation like this. And I'd give you 10 points for that. I'd be very proud of you if you did something like that. But we're capped at 10 points. If you've already done the Euclidean algorithm, or if you read one of the papers and did a paper on it, you're kind of done at this point. Okay, they can ask weird questions like, is the null set, and let's call this thing A. So is the null set an element of A? And yes, it is. Okay. How about is the set that contains the null set an element of A? Or sorry, a subset of A. Let's go with that. Okay. And yeah, it is. Okay. Where is it? It's this guy right here. So a subset of this set is the set that just contains that null set. Sorry if I misspoke there. More weirdness, right? Oh, how many elements are in A? So how many things are sitting in A right now? And one thing they do to kind of say that 2 sets are equal to each other, well, they have to have the same number of elements. So for example, if I have a set that's 1, 2, 3, and then I have a set that's 1, 2, there's no way these two sets can be equal because this set here has two elements, which can be sets themselves, and this set here has three elements. Okay, so there's no way here in this case that C can equal D. So I would say C does not equal D. Anyways, the number of elements in this weird set that I've created, A, is, you can probably guess, there's three elements there. There's this set that contains the null set and another set containing two null sets, which, yeah. Okay. Then there's this set, and then there's finally this set here. All right. There's probably issues like, do you really need to write these three sets as different? So just now thinking about it, we don't repeat elements in our sets. So this is probably all screwed up. But anyways, it kind of gives you a glimpse into the weirdness of set theory. There's other things in set theory that are weird, like Russell's paradox, which you can look up online. That book I was reading on axiomatic set theory uses something called a ZFC, something like Zermelo-Franco axioms plus the completeness axiom, and that kind of cures Russell's paradox. Russell's paradox being something of the flavor: does the set of all sets that contain themselves contain itself? And it's like, well, if the set is in itself, then it contains itself, and therefore, does the set that it's weird. It's like some weirdness like that. I don't want to waste your time proving to you that I can think through it. I don't see what the benefit of that is. But, yeah, it's out there. Like I said, ZSC is a cure for it. How do they cure it? They kind of have to have different definitions for. So they'll redefine a set as a class. So there's kind of this hierarchy of things, right? So they'll have a class, and then they'll have sets, and then they have elements. And they kind of say that everything you see that has those curly brackets is a class. Okay, and then they'll have to differentiate between a class and a set. Like all classes are all sets are classes, but not all classes are sets. And then you can call that set that contains all sets that don't contain themselves a class as opposed to a set, and you avoid the paradox. Okay, so it's some crazy business. It's worth going through, though. It's especially that axiomatic stuff, that axiomatic set theory. It's a lot like when you work geometry and you worked with these axioms, except now instead of working with pictures, you're working with set theory ideas. So it's not geometry, but it's the exact same construction as geometry. Okay. So anyways, that's an introduction to the weirdness going on. Yeah. So welcome to set theory. Okay. So anyways, let's get to what the book has for us and start taking a look at that baloney. First, we'll start with subsets, and we have some definitions, right? So A is a subset of B if and only if for all x and for all x, if x is in A, then x is in B, right? Right. They're not going to define a symbol for proper subsets. They're just going to kind of include the proper subsets in that definition. Okay, so they'll maybe tack on when B has more elements than A, and everything in A is in B, then it's a proper subset. Okay. A is not a subset of B if there's something in A that's not in B. So if and only if there exists an X such that X is in A and X is not in B. Okay. Okie dokie. Set equality. So basically two sets are equal if all the items in one set are also in the other set and there's no extra items. Okay. To prove set equality, the way we always do it, and you'll see this a lot in proofs, you keep taking math, first they show that A is contained in B, and then they show that B is contained in A. Okay? So there's always two parts of the proof. We'll show you an example. Number 7, we have these sets. Okay, so set A is the set of all x in the integers such that x is equal to 6a plus 4 for some integer a. Okay. Set B then is going to be the set of all y in the integers such that y is equal to 18b minus 2 for some b in the integers. So there's questions like, okay, so is A equal to B? And to show that, you have to prove that A is contained in B and B is contained in A. And homework, I don't know if there's one. I don't think there's one of these. It's kind of like just find an element that's not in both to prove that they're not equal. So it turns out that there's stuff in I think there's stuff in A that's not in B. Okay, but everything in B is in A. So I'll try to kind of proceed like the proof, like a formal proof would go. Okay, so the first part we'll say is B contained in A, and then we'd have to show A is contained in B. So to show this, we would take an arbitrary element in B and show it is in fact in A. And then because that arbitrary element is arbitrary, you can say it holds true for all elements. So suppose y is a particular but arbitrarily chosen element in the set B. Thus, by definition of B, there exists an integer, little b, such that y is equal to 18b minus 2. Okay, so from here, what I'm going to do is kind of try to back engineer an element in the set A. Right? I'm going to show that y is actually in A. Okay. All right, so this takes a little bit of cleverness. And so you can think about it, you know, where do I want to end up? I want, for this to be an A, it has to be 6 times something plus 4, right? So 6 times something plus 4. All right, so how is that possible? So if you go 18b, and then I think if we subtract away 6 and then add 6, that'll do it, right? And then minus the 2. So it's that old trick where you're basically just adding in 0. Negative 6 plus 6, this thing is just equal to 0. And then minus 2, right? And we haven't changed anything going from the first step to the second step. So there's no real change. Okay. All right, and then this next step, we can factor a 6 out of these two terms, and then these other two terms, that's just equal to 4. That's this element here. So here we can factor out a 6, we get 3b minus 1, and then we got it, right? So y is 6 times 3b minus 1 plus 4. And then of course you have to say where 3b minus 1 is product slash difference of ints and therefore of an int. Okay. Hence it's in that other set. So hence it's in set whatever, right? Set A. And we've shown then through this element argument that B is actually contained in A, because everything in B you can pull that trick on. Okay, so the second way then is not going to work, right? If it did work, we would want to show is A contained in B. And the way we're going to do it is kind of just pick an arbitrary element in A such that we're not going to be able to rewrite it as an element in B. Okay, so suppose basically that A equals 1. Then consider the definition in set B, right? So then the element y equals what am I doing? Sometimes I confuse myself. So suppose A is equal to 1. I'm trying to show that A is contained in B. Okay, so basically I'm going to find an element in A that's not in B. Okay, so consider then the definition of A way back here, wherever it went. Where are you? Oh, there it is. So the definition of A, I'm going to let little a in this thing equal 1, and then that'll give me an element that's in A, right? So the number 10 will be in A. And then I'm going to show that there's no way to make this thing equal 10 for any integer B. And that will mean that the number 10 is in A but not in B, so there's no way A can be contained in B. Okay, so suppose A equals 1. Consider then the element in set A defined as x equals 6 times A plus 1, right? So by substitution, that's 6 times 1 plus 1, which is equal to 6 plus 1, which is equal to 7. Okay. It's 4, sorry. 4. So this is equal to 10. Okay, so supposing A is a subset of B, we're going to end up with a contradiction, right? So note our attempt to show this element is in B. So supposing this element was in B, we would have the following. We would have that 10 is equal to 18b minus 2, where b is some integer. So we should be able to solve for b in this equation and get that number. So 18b is equal to 12. Divide both sides. B is equal to, and there's the issue, right? The only number that could possibly give us 10 would be a rational number. And if you look back in your definition, everything in B is of that form for some integer value B. Okay, so there's no way this element can be in set B. Okay, so this thing is not an element of the integers. Hence, there is no way 10 is an element of B. Okay. Hence, it is not the case that A is contained in B, and we'll just write that A. So A is not contained in B. So the conclusion, there's no way A is equal to B. Okay, because obviously A has that element 10 and B does not. Okay, so there's that. It's much more easier on the web assigned because you don't have to write out the proofs for people to read or anything. It's basically just find the counterexample that doesn't work and go from there. Okay, so anyways, in the proofs, in the more rigorous proofs, and one other thing maybe I should mention was the old Venn diagrams. The Venn diagrams again fall into the category of being extremely kind of elementary. Okay? So you may have seen the Venn diagrams. Scrolling back here, for instance, A intersect B, right? So you have A, maybe this is B, and A has the elements 1, 2, and the set containing 2, and then B has, let's not put the 2 out of the circle here, get rid of U. So B has the element 2, right? So A and B. Okay, so A intersect B is this region where they overlap. In particular, the number 2 is in A intersect B. Okay, so A intersect B is this stuff. What we're going to be trying to do is show these sort of equalities between different sets. And you don't want to be using Venn diagrams to do this. They're all going to make fun of you, and they will laugh at you if you try to take a real math class. Okay, so you don't want to be using those Venn diagrams. They're kind of in the homework. They're in the book. We hope that you've seen them before. Okay. Our intention is to make things much more rigorous, though, and then using these methods, we can talk more abstractly and not have to worry about pictures, which are kind of restricted to 2 dimensions and can be extremely misleading. So anyways, A union B, the definition is going to be the set of all x in the universe such that x is in A or x is in B. Okay, so the universe is just all elements that are under sort of discussion. Okay. Secondly, then we have intersections. So this is A intersect B, and it'll be the set of all x in the universe such that x is in A and x is in B. Okay. I don't know. I guess we could show the Venn diagrams. I don't want you using them though. Okay, if you're doing a proof, please don't do a Venn diagram proof. They're all going to laugh at you. Okay, A or B is basically everything, right? Here. Then A intersect B, I kind of already showed that to you above. That's just the gunk that's common to both. Okay. 3 then, the difference. So A minus B is a set of all x in the universe such that x is in A and x is not in B. Okay, so let's draw our little Venn diagram, even though I don't want you to ever do this. Okay, and I'm assuming the first one is A, the second one is B. Okay. Everything that's out, everything inside the box is the universe. Okay. So A minus B is this junk. What else? Complements. Complements seem a lot like the negations back in logic. So a complement is going to be the set of all x in the universe such that x is not in A. Okay, so in this case, we'll just have maybe one set to consider. This is set A, and A complement is everything out here that's not in A. Okie dokie. Sure, let's look at a problem from the book. Okay. So probably similar to what you would do in your homework on WebAssign. They give you two sets. Okay. These are intervals. So intervals you can think of as sets. B is the set of all x in the reals such that x is in between -1 and 2. Okay. When I get these, I like to write it all out so I don't have, because some of the problems on WebAssign are so long that you'll scroll away from the original definition. So if you have it written down on a piece of paper, you don't have to keep scrolling back and forth. Anyways, I'll go ahead and plot these guys on the number lines. So I need -3, -2, -1, 0, 1, 2, 3. Okay, so I'll put -3 here. -2, -1, 0, 1, 2, 3. Okay, so I'm going to use a closed bracket to imply that I have included the endpoint. It's less than or equal. So equal bracket. Okay, when you see bracket like that, they'll call that a closed interval. Okay, so in real analysis, they work a lot with closed versus open intervals and worry about issues surrounding that. And what are the characteristics of a closed interval that make it closed? Okay. So the other set, I'll use an open parentheses to indicate we're not including that guy. Okay, and so let's take a look. So A union with B. Okay, so that means take everything in A and everything in B and kind of smush them together. So I'll be going from -3, including that, and then there's an overlap between the two intervals and it goes all the way up to 2. So we could write that as the set of x and r such that x is greater than or equal to -3 and less than 2. Okay. Let's try another one. This is part B. A complement. Okay, so for a complement, well, what is A again, right? So A would be this interval from -3 to 0. A complement is just the other stuff, right? So it's this junk and this junk. Okay. So it's a set of all x in R such that x is less than -3 or x is greater than 0. So one thing, the book tries to teach you things in the exercises, and I was probably complaining in our little lectures at night that don't just blow through the homework. Try to use the homework to learn something, okay, besides doing it as quickly as possible, which is useful. You want to go to sleep and you want to get your work done, you want to graduate, you want to get the job. I get it, okay. But there's stuff here. There's stuff to learn. And I think ultimately, even if your goal is to get a job, you want to train yourself to not just be trying to get through it as quickly as possible. Okay. Learn something, even when because if you just train yourself to get through stuff as quickly as possible, when you get to your job, you're going to still have that attitude. and you don't want it. You don't want that attitude. Okay? Learn something. Take time to smell the roses, right? Okay, so A complement union B complement. Why is this thing important? Well, you kind of wonder about its relationship to this thing, because in logic we had that De Morgan's rule, and we kind of wonder, when you negate an and, you end up with an or, right? So maybe if I take the complement of A intersect B, which is kind of like A and B, I'll end up with A complement union B complement. Are those things connected? And you can investigate that right here. You can kind of look at it and explore it a little bit. Okay, I'm not going to though. All right, so what is this thing? So A complement I kind of already have sitting here in the green, okay, on the left of the screen. B complement, let me maybe attach that to this picture where I drew B, right? So I'll put that in green as well. It's on the right. So B complement is just this stuff. And then what do I want? I want the union of all of that. So I can kind of, in my head, overlap it, right? So I'm going to be first, it's going to be all x's that are less than or equal to -1, or it's going to be all x's greater than 0. Okay, because if you kind of align this to this and see the overlap, you can end up making that conclusion. Okay, so you'll have a lot of that junk to play around with. Let's move on. Okay, something that's definitely comes up in class like real analysis and advanced calculus, and of course some topology, are these things. Okay? The book will take you through the basic intuition. Okay. The thing that you're going to be more interested in is what happens when you take arbitrarily large unions and intersections of sets. Okay. These are usually finite. So for example, number 21, we have these sets C sub I, and in part A, we want to know the union of these sets from I equals 0 to 4, the C sub I. Okay, you can literally write out what these things are. So when I plug 0, so this notation that with the big U thing, this notation I just wrote that I'm going in blue, circling in blue here, that notation is kind of like the summation notation or the product notation. It just means build a sequence of sets joined by unions going from 0 to 4, where I'm plugging 0 to 4 in for I. Okay, so what is it? C0 union C1 union C2, etc. Okay, so what exactly are those sets? So C0 is a set from 0 to 0, 0 to -0. Sorry, it's just two elements, right? 0 and -0. Those are the same, so we're just going to write 0. Okay. C1 is a set that contains 1 and -1. Okay. In the homework, these sets are actually intervals. Okay, a little more complicated, I think. C1, C2 is the set that contains 2 and -2. And how am I getting these numbers? I'm using this formula here, this formula in green, to populate this. Okay, so C sub 3 is going to be the set that contains 3 and -3. And then C sub 4 is going to be the set that contains 4 and -4. And then I just take the union of all those sets, right? So it's just going to be -4, -3, -2, -1, 0, 1, 2, 3, 4. Okay. Okay, so I think it's pretty simple. It's just a shorthand way of writing big unions of a whole bunch of different sets. And all that stuff, it all works the same way, because you can kind of pair them and just use the properties of unions of just two sets, and then you keep on repeating. Okay, so it's nothing new. Maybe the notation is new. Let's look at the intersection from I equals 0 to 4 of C sub I. Okay, So it's the same thing as above, except now we have intersection symbols, right? Okay. If you allow me to, let me just abbreviate with my dot dot, my yada yada yadas. Okay. Okay. So what's the intersection? Well, there's nothing in common here. Okay. So the intersection is just the empty set or the null set, right? When this happens, we call them mutually disjoint. They have no items. Well, in particular, it's not just that if you have an intersection of sets and the set is empty, it may or may not be mutually disjoint. Mutually disjoint is kind of a hardcore. There's no way for any two sets to have anything in common. So it's not just that all the sets have nothing in common, but if you were to extract any two different sets in this sequence of sets and take their intersection, there's nothing in common there. Okay, so I'll say first, the question in the book is, are the sets mutually disjoint, right? And yes, they certainly are, because for any intersection of two sets, C sub I intersected with C sub j, and I not equal to j, so for C sub I intersects C sub j and I not equal to j, C sub I intersects C sub j is the null set. Okay, so it has to work for every possible pair of sets. Okay, and that's what they mean by mutually disjoint. Okay, let's look at some more realistic type unions and intersections you may see. So the union of the sets C sub I from 0 to n, you have the set negative n minus 1 at the end of the day, right? So what the heck is this? Let me erase that and kind of do piece by piece, right? What the heck is it? It's sorry, the stupid pen wasn't working. So first you have the set 0, and then your union with the set negative 1 to 1, negative 1, 1, and then you have the set negative 2, 2, all the way up to the set negative n comma n, right? And if you union all those together, you just get negative n minus 1, dot dot dot, all the way to negative 2, negative 1, 0, 1, 2, dot dot dot, all the way up to n. Okay. An infinite one, so I'm going from I equals 0 to infinity of C sub I. None of these sets will have anything in common, and it's basically because of part B and part C. Basically, every set is different, right? In particular, we'll note C sub I would equal negative I comma I, and then C sub j, and maybe I shouldn't use C sub I, but hopefully you get the picture. Negative j comma j. Thus, C sub I intersects C sub j will be empty whenever I does not equal j, which means they're mutually disjoint, right? So at the end of the day, this intersection won't have anything in it. Okay, when you take real analysis and advanced calculus and topology, some of the issues that come up have to do with closed and open sets. So there is like something like this, the intersection of the intervals negative 1 all over I comma 1 over I from I equals 1 to infinity. Okay, so what would that be? It's like what do we have? -1 to 1 intersected with, and these are intervals now, not just 2 points. -1/2 to 1/2 intersected with -1/3 to 1/3 intersected, blah blah blah, on and on and on forever. Right. So what we have in advanced calculus and real analysis, there'll be all these theorems about sequences, and there'll be tons of theorems about closed sets and open sets, and it turns out there's something called the nested interval theorem. And that's in advanced calculus. And then I think there's another one like the Cauchy nested interval theorem, which is in real analysis. And what they say is basically if you have an intersection of arbitrarily countable number of closed intervals, then that intersection is not empty. Okay, so basically if you take this intersection that I just wrote out here in the green box, it's going to have one element inside of it. You would prove it using sequences and imps and soups and stuff like that, probably. I don't remember off the top of my head, it's been a while. But the nested interval theorem says it's going to have something in it. And in particular, in this case, that something is going to be, well, you kind of have to, at this point, guess, right? So here's -1, here's 1, right? That's that interval. And then these sequences have to be nested. In other words, they have to be inside of each other and decreasing or something like that. Right, so you see how -1/2 to 1/2 is inside of -1 to 1. You have to have that criteria hold as well. And then here's -1/3 to 1/3. And there's going to be one number that gets smushed in there. And you at this point will have to guess what that number is. And I hope it's obvious. The number that is in the intersection is just 0 in this case. Okay, so you would write the set containing 0. Okay, I don't think that she talks about it in the book, but that's what it's about. Okay, we're super interested in whether or not intersections of closed intervals are closed. Are the unions of open intervals open? Is the infinite number of is the intersection of a countably infinite number of closed intervals closed? There'll be tons of questions like that. Okay, and you'll have to use set theory to kind of with advanced calculus techniques to prove these things to be true or not. Okay, so I just wanted to note that because it's clearly something that is an issue in the homework. Okay, so partitions now. Partition. So a set of sets, basically. The set of sets A1, A2, A3, etc. is a partition if you have two things holding. So first, A has to be the union of, so this set of sets I'll call A is the union of all of the sets inside of it. Okay, and then secondly, they're mutually disjoint sets. Okay, so you do this with that mod stuff, that mod arithmetic. So an example, quotient groups. Okay, so we see these things sometimes. Hopefully this doesn't blow your mind or anything. The quotient group Z3Z is basically just a way of kind of cutting up the integers into a bunch of into just 3 numbers. Okay, so the problem with the integers is that there's an infinite number of them, and working with an infinite number of objects is not a lot of fun. Okay, so one trick you can do is to turn the integers into a finite set. and you do this with that mod arithmetic stuff. So the quotient group Z, sometimes call it mod 3Z, is equal to the set of sets. And what are those sets? And they call them classes. Okay, the class 0 is a set of all Q, I'll say, such that Q is equal to 3 times n for some integer n. Okay, and it's really just well, you know, -9, -3, -1. You take the integers and you multiply them by 3. So dot dot dot. Whoops, this should be 0. Sorry. Okay, and then this class 1 is the class of all integers q, such that q is equal to 3n plus 1 for some integer n. Okay, and what the heck is that? Well, that's just going to be the set of all those integers plus 1. So -8, -2, 1, 4, 10. Okay, and then the class 2 is going to be a set of all integers q, such that q is equal to 3n plus 2 for some integers n. And in that case, it's just going to be -7, you know, dot dot dot, -4, or is it -3, or -1 rather. Okay. -1, 2, 5, 11. Okay, and this forms a partition of the integers. Okay, every integer is in one of these sets. Every integer is of the form 3n, 3n plus 1, or 3n plus 2. You tell which set it's in just by taking that number mod mod 3, right? So 11 mod 3 is 2, right? And clearly that means it's in, this guy is in that class 2. Okay, the set 2 of things that are described by 3n plus 2. So in particular, you could even find that n. It's 3, right? Okay, so it partitions an infinite, the use of it is to partition an infinite set into a finite number of elements. And then you just play around with that finite number of elements. You can learn a lot about how things are ordered within that infinite set. Okay, so there'll be that stuff. You can even just rewrite the numbers as even and odd numbers. The even and odd is a partition of z. Okay, so number 28, they even ask, is E, O, so even, E for even, O for odd, a partition of the integers. And yeah, it is, because every number in the integers is either even or odd, and there is no number that is both even and odd. You may wonder about 0, but if you remember the homework in the even and odd section, 0 is even, okay, because it's 2 times some integer. All right, power sets, I don't remember seeing them in the homework, but they're kind of a big topic in set theory. When you begin with ZFC set theory, the power sets are really kind of your only sets in the beginning. So everything else is a class, and you only have certain kind of items that are sets, and they're not really even defined. They're just kind of forced into existence via laws or via axioms. It is some intense, powerful stuff. But what is a power set? It's a set of all subsets of a set of all subsets. Okay, so for instance, if we have the set A, which equals 1 comma 2, the power set of A, which you'll write with a cursive P, is going to be the set that contains all subsets of A. So the null set is a subset of all sets, and then you have the set containing 1, and then you have the set containing 2, and you have the set containing 1 and 2. Okay? And each one of those 4 sets is a subset of A. Right? In particular, the number of things in the power set, so you can kind of check to make sure you got the right answer. The number of things in the power set is always going to be 2 to the number of things in the set A. Okay, so maybe I should rewrite this. 2 to the number of things in A. So in our case, the number of things in A, if you just, sorry, the number of things in the number of things in A is 2, right? So the number of things in the power set should be 4. And clearly, if you look back, there's 1, 2, 3, 4 things. Okay, okie dokie. Let's look at Cartesian products. Okay, there's weirdness about ordered pairs. Ordered pairs are really sets, but they're kind of have to be defined weirdly with a set. So if you want to define ordered pair with a set, you'd probably have to do something like this. And there's more than one way to define an ordered pair, but this is kind of like the standard way right here. Okay, using sets to define it. So in the construction of ordered pairs, you'll have to go through that kind of construction, and eventually you'll just kind of settle on this notation for ordered pairs, where 2, 3 is not the same as 3, 2 is kind of what I'm getting at. So the ordered pair 2, 3 is not the same as 3, 2. Okay, that's not true in sets, right? The set 3, 2 is exactly the same as the set 2, 3. Okay. If you use this notation, then it's no longer kind of an issue. You can always tell, you can always describe them as which is which. Okay, so anyways, ordered pairs is basically what we're talking about here. We'll give a better definition of it in the next section, but let's look at one of the problems. So 31, we have the set A is going to be 1 comma 2, and the set B is the set 2 comma 3. Okay, so A cross B, which is a Cartesian product, is going to be the set of all ordered pairs where the first component is from A and the second component is from B. Okay, so 1, 3, and then we have 2, 2, and then we have 2, 3. Okay, so it's some other junk. What else do we? Let's just take a look at this problem. Let's look at what the heck is A intersect B, right? I think that's just number 2. Part B. What's the power set of A intersect B? That's a set that contains the null set and the set that contains whatever's in A intersect B. Okay, so 2 to the 1, right, is the number of things in the power set, and in this case there's 2 things there. So okay, let's skip around a little bit. Oh my gosh, the power set of A cross B. That's part D. Okay, this might be a bit ambitious. We'll leave it at this. This will be my last problem. I've gone on enough. Power set of A cross B is going to be the set of, so what was A cross B? That's above. So it's a set that contains the null set. That's a set that contains just 1, 2, and then the set that contains just 1, 2, and 1, 3. Oh my gosh, this is going to be ridiculous. Let's not. Well, I'll just give you a couple of them. I'm not going to go through all of them. I want to be a little bit more systematic. So all the sets that just contain one element, right? So there's all those. How many are in there? First off, it's going to be 2 to the 4th, right? Because there's 4, 1, 2, 3, 4 items and A cross B up there at the top. Okay, so 2 to the 4, 2 times 2 is 4, times 2 is 8, 16 things. Oh my gosh. Okay, so there's the sets that contain one thing, then the sets that contain two things. Okay, and then there'd be some more of those, and then you would get to the sets that contain three things. Okay, more of those, and then you would get to the sets that contain four things, and there's only one of those. That's just A cross B. Okay, okie dokie. And there should be 16 things in there if you go through it. We'll leave it at that though. Hopefully I didn't butcher anything. If there's any set theorists for whatever reason watching my videos, first off, stop watching my videos. You should be doing something else with your life besides being a critic of a community college teacher. Um, if you're interested in more set theory, by all means, don't consider what I say the gospel on the subject. I'm just, like I said, a community college teacher. I've studied it. I didn't do a PhD on it or anything like that. But yeah, so there's great books on the subject if you want to investigate things like these sets within sets within sets and Russell's paradox and the ZFC axioms. Just send me an email and I'll give you a reference to a good set theory book that can explain this stuff to you in more detail. Okay, and probably correct half the things that I was going on about that's not in the book. So if I said something that's not in the book, take it with a grain of salt. It's been 20. How long has it been? My God, it's literally been like maybe even 20 years since I was in grad school. So it's surprising I remember any of it, to be honest. But okay, so we'll leave it at that. I hope you have a good day, and see you next time.